Next thing that we are going to use is Snell's law. Whenever or wherever you would look for refraction, you would find Snell's law. A Dutch physicist named Wilbrord Snell derived the relation between the different angles of light as it passes from one transparent medium to another. And the relation that he derived is the index of refraction or refractive index multiplied by the sine theta is equals to the index of another medium and the sine theta formed in another medium. And to differentiate these mediums, we would say index I multiplied by sine theta I and index R multiplied by sine theta R. So this is what we are going to use. And we at least have two values of this equation which we already know. We know sine theta I, which is the magnitude of I opposite. We know sine theta R, which is the magnitude of R opposite. So let's start applying these values in this equation. So index I, refractive index of the medium in which incident ray is traveling, multiplied by magnitude of I opposite, equals to index R, the refractive index of medium in which refractive ray is traveling, multiplied by magnitude of R opposite. And let's give the sign of vectors to both of them. Let's bring the refractive index R on the other side of the equation, which gives us index I divided by index R multiplied by I opposite is equals to R opposite. So now we know one more thing, that the direction of I opposite and R opposite is the same. If we look back to our original diagram from which we isolated these two triangles, this is I opposite and this is R opposite. And the directions of both the vectors are same. And that is why we can write this equation as index I divided by index R multiplied by vector I opposite. No magnitude, just vector. Because their directions are same, we can change this equation to R opposite. So this way we have at least one component that we need to find out R vector, because we know that R adjacent plus R opposite equals to vector R. So we know the vector R opposite, and now we will find out R adjacent, and we will tag this equation as equation 4. So now we have 4 equations in this derivation, and now what we will do is in one section we will perform the calculation of this triangle, and in one section we will perform the calculation of this triangle. So second component of the equation that we have to find out is R adjacent. And we know that R adjacent is a projection of R onto vector negative n. So projection can be represented as projection of R onto negative n. And the formula for that is vector R dot negative n vector multiplied by negative n vector. As we have been doing several calculations of dot product of two vectors, and as we know that the dot product of two normalized vector is the cosine of the theta between these two vectors. So vector R dot negative n vector can be represented as cos theta R, because theta r is the angle between vector r and negative n vector. And then we multiply it by negative n. So this is the projection of r onto negative n. Similarly, we do the same thing for the other triangle. I adjacent is the projection of vector I onto vector n, which can be written as projection of I onto n, vector I dot vector n multiplied by vector n. And similarly, this becomes the cos theta I multiplied by vector n. So this becomes the projection of I onto n. We will number this equation as 5a and this equation as 5b. And in the beginning, we understood 4 tools that we are going to need in this derivation. And we will take out the tool at this point, which is sine square theta plus cos square theta is equals to 1. And when we will apply this equation here, we would replace the cos theta with 1 minus sine square theta. So the projection of r onto negative n becomes, because this is a multiplication, we will first write negative n vector